So X-ray crystallography is an important tool in learning what the structure of solids are, especially crystalline solids. And when we say crystalline solid, we mean a solid that has long-range order to the atoms, molecules, or ions. Crystalline solids often have beautiful shapes. Minerals will make solids like this. This is a close-up picture of a snowflake. So water also forms crystalline solid as ice. So how can you tell how those atoms and molecules are arranged? By using the interference of electromagnetic waves. So we talked about this when we were talking about the wave-particle nature of light and of electrons. When we have electromagnetic waves, they can interact constructively or destructively. And this can happen when you pass a light through two slits separated by a distance that's similar to the wavelength of the light. And you get an interference pattern. Remember the guy with the box on the beach? And he was showing people this rainbow. So here, instead of using visible light, we're using X-rays, because X-rays have wavelengths that are on the scale of the distances between atoms in crystals. So we're taking the X-rays and focusing a beam of X-rays on the crystalline solid. The particles, the atoms or ions within the solid, act as splits. Splits, where did that word come from? The slits are from passing between the atoms, okay? And so by passing between the atoms, diffraction patterns are made and can be seen on a detector. The spacing affects the diffraction patterns that are seen. And I'll be flat out honest with you, how they get this and figure out the distances between them, I never learned how to do that. That's just kind of crazy stuff, but they can do that. This part makes sense to me. So here we have two rays or waves that are in phase, okay? And passing between the atoms causes them to bend, right? And the path difference here, from here to here, this one wave goes this much farther than the other because it does this part. Let's highlight that. It goes from here to here, farther than the one that bounces off the top atom. And you can calculate that using Bragg's law. So in Bragg's law, there's an integer times the wavelength is equal to 2d times the sine of theta, where d is the distance between the atoms. So what they do is they'll twist the solid at different angles until they get the constructive or destructive interference. And by looking at that angle, they can determine the distance between the atoms. So this whole calculation here is just a bunch of geometry, really. But this is Bragg's law, and you may need that for some homework problems. So typically, they find the angle that gives constructive interference just by moving things around, and then they can calculate the distance using this rearranged version of Bragg's law. So X-ray crystallography has been very important. This is an example of an early result, and it's kind of hard to imagine how that's going to really tell you much, but it does. X-ray crystallography was instrumental in determining the double helix structure of DNA. So that was a pretty big deal. Can also be used to look at proteins and enzymes and other different biologically important molecules, in addition to just regular ionic compounds. So this is an example of a Bragg's law problem. The spacing between layers of molybdenum atoms is 157 picometers. Calculate the angle at which 154 picometer X-rays produce a maximum reflection for n equals 1. So this is using Bragg's law. The wrong pen there. N lambda equals 2d sine of theta. And here they are asking us to find the angle. I lost that. There we go. We're supposed to calculate the angle, and the information given is the distance between the layers, that's d, the wavelength, and the value of n. So let's just identify those things. So the distance between the layers is d, that's 157 picometers. The lambda is the wavelength of the X-rays, 154 picometers. N is equal to 1, and we're solving for theta. So we would need to rearrange this equation. Well, we can divide both sides by 2d and get the sine of theta is equal to n lambda over 2 times d. So let's plug the numbers in there. So n is 1, lambda is 154 p.m., and we're dividing by 2 times 157 p.m. The units here are going to work out as long as the units of wavelength and the distance between the layers is the same. So I've got 1 times 154 divided by 2 divided by 157. So this is 0.49, 0.44, 3 sig figs, right? So we'll call that good. Because these are measured distances and they're not exact. So we haven't used sine in chemistry before. Do you remember learning about that in math class? Sine, cosine, tangent. Sine, cosine, sine, 3.14159. That's what I always think about. Anyway, so sine is a function like a logarithm is a function. And so to undo the sine, we have to do what's called the inverse sine. So there's a button on your calculator. There should be a button that has, it actually says sin, S-I-N, and S-I-N to the minus 1. So what we want is S-I-N to the minus 1. Theta is going to equal the inverse sine of 0.49044. Oops, wrong button. So on the 36X Pro, the way you get that inverse sine is you press that button twice. The first time it gives you sine, the second time it gives you inverse sine, and you type in the numbers and press equals, and we're going to get 29.3695, and the unit there is degrees. I have no idea what the sig fig rules are for sine. Let's just go with 3, since that's what we started with. So let's just call this 29.4 degrees. So for this particular substance, an angle of 29.4 is going to give you maximum interference. Any questions?
As long as the distances are the same unit, you're okay.
Right. Yeah, as long as the wavelength and the distance are the same unit. They could be meters or nanometers or anything. Yeah. Oh, 29.4.